Hi everyone, I'm Benny, and today I'm going to switch the topic a little bit around and talk about a SNARK system that I've been working on recently. So you might ask, what is a SNARK system? Well, SNARK is a cryptographic tool that enables a slow but trusted verifier to outsource a computation to a fast but malicious prover. To achieve so, the verifier first invokes a trusted compiler to convert the program into some form of a representation that a proof system operates on. Next, the prover executes the program together with a representation in the proof system to emit the output of the execution and a proof on the correctness of the output. Finally, the verifier checks the proof in time sublinear to program execution and decides to accept or reject the output based on the proof. Now, this trusted outsourcing process is the backbone to the scalability and privacy of our modern crypto industry. And as a result, building an efficient SNARK system is always a priority to the blockchain community. However, today I'm going to take a rather unorthodox approach and talk about an often overlooked aspect of the SNARK system called the execution model. So conceptually, the execution model is the interface between what the program means and how it is executed. Now, if we think of a traditional computer, its execution model includes an instruction set to represent the program, and then things like registers, memories, and calling convention to actually execute these instructions in the CPU. This actually also applies to a SNARK system, where we notice that almost every existing SNARK system employs one of the two execution models, direct translation or CPU emulation. These execution models are more of a consequence of other parts of the SNARK system design than a deliberate choice by themselves. However, we observe that by carefully designing an execution model for the proof system, we can achieve much better improvements. So first, let me briefly go over the existing two execution models and show why they are not optimal. In direct translation, the execution model is the direct implementation of the program in the proof protocol's constraint formalism. In other words, it takes in two things, the flattened version of the program and the heap memory to store all of the array contents, and it compiles them into a fixed set of a constraint unique to each program. So to actually prove the correct execution of the program, the prover would provide an assignment to the constraint that correspond to the execution, and the verifier checks that these assignments indeed satisfies the constraints. Now, since these constraints are program specific, this means that direct translators can allow compilers to apply optimizations that transform at least parts of this program into a more constraint-friendly form, and as a result, make the proof more succinct. However, the downside of direct translators is that these constraints need to be fixed at compile time and has to take into account every possible execution path of the program. In practice, to produce them, the compiler will have to unroll all of the loops, inline all the function calls, flatten all of the if-else branches. And to produce the prover also has to pay for all these unexecuted iterations and branches, which introduces wastefulness into the process. And furthermore, this compile time now also scales with the program runtime rather than its description, which is not how a typical compiler works, and that's way less efficient than what we expect from that. The counterpart to direct translators are called CPU emulators. As the name suggests, it emulates the behavior of a CPU and also adopts the execution model of the emulated CPU. This includes components like an instruction set, instruction memory, some kind of a memory hierarchy, things you expect from a computer, and they're together compiled into a set of constraints that encodes a CPU's fetch, decode, execute loop. Now, programs in a CPU emulation are expressed as a sequence of executed instructions. The prover uses the constraint to prove that it has executed every instruction correctly, and as a result, the entire program correctly. Since the program is expressed as a set of executed instructions, this means that the prover no longer have to deal with all these unexecuted ones, so that solves the problem with the direct translators. However, since the constraint now encode a CPU rather than individual programs, so obviously the CPU emulators can no longer apply some kind of a compiler that does program-specific optimizations. And furthermore, despite how the creators of CPU emulators will try to convince you otherwise, a CPU is still very different from a proof system. If we want to blindly apply an execution model for a CPU into a proof system, that results in overheads in things like instruction memory, register handling, and the usage of call stack, and all of that makes CPU emulators less efficient than what a SNARK system could be. And it is with the benefit and drawbacks of the existing system that inspires our design. We ask, is it possible to come up with a compiler proof system co-design with an execution model optimized for the proof system such that it allows constraint level optimizations, avoids wasteful CPU state representation, and avoids paying for unexecuted computation. Well, obviously the answer is yes since I'm standing here, so let me tell you how CoBBI actually does that. So CoBBI represents a program as a control flow graph of small individual program chunks that we call them blocks. Its execution model is consisted of a sequence of executed blocks, together with a scope stack that's optimal for the proof system and our regular heap memory. And these components are compiled into a set of constraints that verify a block's execution and the transition between blocks. There are three main aspects in CoBBI. The first are the blocks, which are constraints tailored to straight-line program chunks with unlimited number of local registers. The second is a block-to-block transition, where data can be passed through either non-local registers or these stack abstractions that's specific for each program and optimal for the proof system. And also the size of the block and the exact content of the block-to-block transition is controlled by a compiler that does program-specific decisions. And finally, we have the block trace, which enables the prover to express the computation through a sequence of executed blocks. Note that the usage of block enables CoBBI's compiler to apply constraint-level optimizations, at least to individual blocks. CoBBI's block-to-block transition is a much more proof-friendly representation than whatever a CPU is doing. And finally, the usage of block trace enables CoBBI's prover to only pay for what it executes. Now, CoBBI is still very far from its ultimate form, but it is already showing huge potential. We compare our current version of CoBBI against the state-of-the-art direct translators and CPU emulator, and we have shown that CoBBI has been generally outperforming them. If you're interested more details into these data or how the current implementation of CoBBI works, we have a paper that's accepted just now in Oakland 2025, so feel free to check that online or ask me any questions if you want. And finally, for the next step of CoBBI, we come up with two main areas that we think requires further improvements. The first is on compiler optimization, where the current compiler of the CoBBI has already been performing a lot of SNARK-specific optimizations, but we feel like the compiler is still restricted into the traditional framework, which is that we have to respect the execution order of the program. But if you think about how the verifier checks an execution, like the proof of an execution, it doesn't have to do that from the very beginning. It can start from anywhere it wants. So if we also allow the compiler to try to reorder the things around, we believe that can make CoBBI even more effective. And the second thing is on proof technique, where almost every modern CPU emulator has adopted this powerful technique called lookup arguments, which enables it to efficiently check CPU instructions that are otherwise unfriendly to constraint representation. We believe these optimizations can also be applied in CoBBI, but how exactly do they fit into our execution model? That requires further investigation. With that, I conclude today's talk. Thank you very much. I'm happy to take questions.